So highest, 0.79. I'm sorry, highest 0.93 minus the lowest of 0.79, 0.14. That's the range. It's the difference between the highest and the lowest. So mode, it's just the one that is the most common. Anything that repeats is suspect. 3 repeats seems to be the most, because there's 3 3s and then there's 2 5s. So the mode is 3, because 3 repeats 3 times. 5 is the only other one that repeats. It repeats twice. Okay. The mean here, so Alice sells boxes of candy and wants to know the mean number of boxes she sells. The number for the game so far are as such: 16, 14, 14, 21, and 15. So we're just going to add them all up. And then it's 1, 2, 3, 4, 5. So 16 is the mean number. So on the average, she's selling 16 boxes every game. All right, so given the following list of prices and thousands of dollars of randomly selected trucks at a car dealership, find the median. So the median is the one where we've got to find the middle value. But before we do that, we got to make sure the data is ordered. So it doesn't appear to be ordered because I see a 14 here. So let's order it. And then 26. $42. So here we've got them ordered now, lowest to highest. So there are 1, 2, 3, 4, 5, 6, 7 values. 1, 2, 3, 4, 5, 6, 7 values. So since there's an odd number of pieces of data, there's going to be exactly 1 in the middle. And here is that 1. 3 on either side. The 26 is in the middle. So 26 is the median. Now, if we had an even number of pieces of data, there's not going to be 1 in the middle. You would go to 2 in the middle, and then you add those up and divide by 2. Okay. The mid-range, not really all that important, but I did tell you about the midpoint when we were dealing with the frequency distributions and being able to calculate the mean. So it's the same calculation. We just got to find the high plus the low. Plus low. And then we're going to divide by 2. So let's see if we can find the high. The high is 65. So there's your high. And then the low looks to be 50. Nope. It's 43. So then, looks like we get 22, but let's double check. 65 minus 43 is 22. Okay. Mid-range. Same thing as the midpoint. It's the middle value in the middle. And essentially what you're doing is you're just adding up the extremes and dividing by 2, finding the mean of those two. Okay, so this is just to show you that what you do to each data point is essentially the same as doing it to the final value. So the median of this data set is 48, and we didn't want to half each data point. We don't know what the data points are, and then subtract by 4. Well, if we did that to all of them, that's the same thing as just this. 48 divided by 2 minus 4. So that's going to be 24 minus 4 is equal to 20. Okay, so mean, median, and mode. If the data is, if there's no extreme values, then the mean and median and mode should be more or less the same. All right. But for this one, it looks like all the data set are in the I'll tell you what we're going to do. We're just going to do all 3 of them on that. Because it doesn't look like there's really much in the way of extreme values. So I think it's the mean, but let's double check it. And that's 1, 2, 3, 4, 5. Divide by 10. So the mean is 33.2. So the mode, let's see. Looks to be 32, right? Because there's 4 32s, and there's only 133, 136, and 2 34s. All right, and we said that there's 10 of them now. So now watch the way we do this median here. We gotta sort them. See if I can do it like this. So I think that we got it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So now here's how we do the median when we've got an even number. Even number, the n is 10, okay? All right. There is not one middle number, but there's two middle numbers. All right. 4 over here, 4 over here. So that leaves 2 in the middle. So the median is 32 plus 33 over 2. Let's see, that's 31. Add the darn thing up. So that's 65. No, no. 32 plus 33. Oh. Mode. The mode appears 4 times, and the median is almost 32, and the mean is one that's off because of the 32, 36 is stretching them up. If we'd had like another 31 to pull down, then the mean would have been about the same. Okay, so measures of central tendency again are affected by outliers. So the measure of central tendency, the mean is 104.25. Oh, here's the data up here. The data set below represents bugs found by a software tester in her product during different phases of testing: 88, 84, 81, 94, 91, 98, 98, and 200. So they're going to give us the mean, the median, and the mode. Now, because this one has that outlier, see that? That's much higher. It could also be a much lower value than the other ones, but all of the other ones are 80s and 90s. And as I said before, if you have a test average of B, let's say you got 3 tests and they're, got an 85 average. If you score 100, you may well be able to pull it up to an A. But if you score an F, it could well pull it down to a C or even lower. So that's the way that outliers work. So the one that's affected by the
This is
what was the
one of the
question?
ones that I struggled with.
The outlier is 200, and the mean is affected by the outlier because that mean causes it to pull up higher to 104. If you had another value there, let's just say it was 100, then that mean is not going to be as high. It'd be closer to these other two values. What was it? What did you say, Randy?
This is one of them that I struggled with. I just could not get this. I don't know what it
the
was.
Mean,
remembering how to get the outlier or what.
Well, let's see if we can kind of find a way to frame it. Let's do let's do the adding without that outlier. I'll just show you. You know it's an outlier now that I told you, but you wouldn't know what it is. But it's the highest one. All right. So how many do we have? 1, 2, 3, 4, 5, 6, 7. So divided by 7. So 90.6.
So it's like
So
finding
if it
the
didn't
mean.
have, what's that?
I said, is it like finding the mean when you add it all together and divide by itself?
Yeah,
How
that's the mean.
are you?
So
Okay.
what they did is now, let's so we go back to what we had, and if we add that 200 to it, and then divide by 1, 2, 3, 4, 5, 6, 7, 8. See how it pushes it up. That one value makes it jump up from 90, almost 97 to 104 in the median. And
And
generally,
why?
when you have an outlier, that's the one that it's going to affect is the mean. Mean is what we call sensitive to outliers.
And you would add the 200 to the mean?
No, I just added them all up and divided by
By itself.
1, 2, 3. I did it with and without the 200. In other words, I added everything but the 200 and then divided by 7. And then I added all of them and divided by 8. And you see that the mean jumps up to 104.25. See, it jumps up 8 points because of this guy here.
Okay.
The mean is sensitive to extreme values. And see, if we didn't have the 200, then there's not really, I mean, they're talking about 98 up here. Well, 98 is almost what the mean comes out to without the 200. So that's not affecting it. So the mean is what's being affected. That 200 causes it to jump way up. All right, so just the shape of the data. Basically, if it follows the pattern of starts out low, gets high in the middle, and then comes back down, then this is what we consider symmetric data, normally distributed data. So if it was skewed, there would be a real long tail. Like if you took that tail next to that 16 and yanked it and caused everything to pull to the right, or you could also do it on the left. But this right here is symmetric because it's got this nice shape to it. It's not a perfect drawing, but that's the idea of the normally distributed data. The normally distributed data follows that pattern like this here, see? Starts out low, gets a peak in the middle. So that right there more or less follows that. All right, so find the mode of the following data set, which represents result of 200 people. So here's 200 people. We got 125, and then 50 is 175, and another 25. So the mode would be the one that appears the most. There's your mode. It's got the most. All right. When you got words and stuff, it works the same way. You can still have a mode. You can't really have a median for something like that or a mean because of the fact that there's no numbers or there's no values. But with a mode, it's just the one that appears the most often in the data, and you can have numbers or situations like this where it's just discrete values, we call them. You okay with that, Brandy?
Yes, sir. That I understood. A lot of those understood. I think it came from like I had it up and I accidentally, what was it, the position one for homework?
Well, position is related is basically z-score, the standard deviation
Oh
and
no.
such.
So I got that one, like Z-score and all that. What's the one?
Yeah, z-score is a measure of position,
It was
and
the
then the standard deviation
keep going.
is
Sorry.
measures the variation.
I think it's the one where you would have to put in, it was two numbers that you had to put in. And it was from one side.
All right, well, we'll get to it.
I'm gonna find it for you and I'm gonna send it in the chat because that's the one that really
Okay.
stuck. To move
But is
on.
it on here or is it in one of the homeworks?
Let's
Just wherever you get it. Yeah, send it.
Yeah.
I'm just going to keep going. All right. So the table below shows the mean and standard deviation in seconds of all finishers in the mile finals of the men's 1,000 meter race in 2008, 2016. Most consistent. Okay. Now, whenever we have data that's clumped together, in other words, not very well spread out. Oh, let's see here. I got it in here somewhere, the little drawing. All right, should be right in here. Okay, so looking at the green one, we can see how it's spread out. In other words, it's got extreme values, or it's got a lot of values all the way from way out here to this side. All right, so it has to be very fat, and that's what the standard deviation measures. The opposite one would be the one that's real skinny, the red one. So the standard deviation is smaller there. So the smaller the standard deviation, it means the more clumped up it is. And thus, when they're asking about this, the most consistent, then in the year, then it's this one here, because that's the smallest one. So 2016, because the standard deviation for the year is smallest. That's what determines spread. And in this case, that spread relates to consistency. It's not talking about the mean. The mean is the central. It's a measure of center. All right. So a small company decides to investigate the amount of sick leave taken by its 7 employees. The observation are recorded in the data below. Compute the population standard deviation. Okay, so we just got to remember, and I think this one only does the population. I don't think they ever give you the sample, but we'll just remember the sample standard deviation is the one where you got to subtract in the denominator 1 from the value. So for this one, it's this one. Sigma, that's what that is. It's not a 6. So it's x minus the mean, all squared. Then we sum those up. And then we're dividing by n. 1, 2, 3, 4, 5, 6, 7. So n is equal to 7. So the mean, 0 plus 0 plus 4 plus 1 plus 0 plus 6 plus 2. So 10, 11, 12, 13 over 7.
This one has me
Oh,
wrong.
wait a minute. What in the world am I doing? I saw your problem there, Brandon, and I got.
Yeah, but that one
So
also,
this is
the
it.
one
It's
you're
not
working
square root.
with right now is
This
actually,
is right. I don't know why I throw it in the. Yeah, I'm gonna finish it. But check those. What happened to the darn? Go back this time. Check and make sure I got those added up right. I was just a little bit disturbed by the fact that it wasn't coming out to 14. That's why I want to double check. It's not that it ever has to always be even. It's just that it would make it a lot easier if it is.
mine says 13.
Okay, it is 13, right?
Let's see. Yeah, 13.
All right. So 13 over 7, it's a little bit less than 2. So let's go ahead and do it. We still got a little bit to go.
1.85.
Yeah. So see, that's what I was hoping wasn't going to happen, but it says to round to the nearest tenth. So we got to go back past that. I'm going to go past a couple. So this is an approximation now. So that's why that's changing that to a squiggle. All right. So thankfully, we got some zeros in there. So that's going to make this a little bit easier. So what is that when you got up there, Brandy? What is it? I'd get.
And I
It
noticed
just
that
kind of
it's
looks
not
like.
on the review. Not a problem like this anyway. So I don't know how important it is.
Let me just look at it so I
that
can be
was
thinking
on the
about it. Oh yeah, I couldn't take Chebyshev's out. Yeah, I'll show you. It's really this almost the same thing as the other, the empirical rule, but yeah.
Like I got stuck on it for a while, so I had to move on and go to the next homework.
Yeah.
I was like,
Yeah.
I couldn't get it. If it's not as
Yeah.
important,
Whenever you got,
that's about it.
yeah, this is more important. And you got to also realize that when you got an approximation, it makes all this longer, which is,
Mm.
like I said, I was hoping that that was going to be 14.
So this one, the one you said about Sigma, I haven't came across this one, I guess, because I was kept getting stuck on that one and all that, so I had to move
Well,
on.
it's the standard deviation. Like I said, there's another one called the sample standard deviation. I did not see it in here, but the only difference is just a difference of one. So right here, instead of dividing by 7 on the last step, second to last step before you take the square root, is you do n minus 1. I don't remember seeing it.
I did. That's why I was wondering, like, how do you know how to do this
Well, it says sample. It's a sample, and
sample?
here it says population. So if you've got a sample, then you've got to do the n minus 1 division before you do the square root. But this part is still the same. It's 5/7. All right. And then this is going to be them squared here. All right, so let's see if I can do this with a calculator. All right, so 0 minus 1.857. So we're going to square that. And I'm going to put it in there. All right, 4 minus. Oh, oh. I was trying to cheat and use the calculator. Let me go ahead and just write them down. Like I said, when you got decimals, it's more of a pain in that because you got to go a few past what you're going to round off. So this is going to be the same for these. So then we're going to square that. And it's just one of those calculations. If you're doing it by hand, it just takes an incredibly long time. And then this one's going to be the same as the one up at the top. And then the last one. All right, so I'm going to go ahead and add these up.
For the top ones, it says 0 minus 1.857. And it says on the second one, 1.89.
What about it?
Or is that a 5?
It's the value over here, 1.857. I messed up over here in writing it, but it's the one that's over here. See that?
Okay.
Okay, so 32. So then this is so sigma is the square root of shucks, I was trying to get that value back and it went away. This has got no back on it. All right. This may be messed up now, but that's generally what it is because I didn't get to write down the third decimal, but it might be enough accuracy. So then 32 point. So 2.2. 2.2. Because it says one to the 10th. All right. All right. So for this, just remember it's the same old thing. If the graph is spread out, which is what this is called just a what is it? Whisker and whisker plot, box and whisker plot. I think I call it. They call them other things too, but it asks about the one with the highest, the smallest standard deviation. So naturally, it's going to be one that's the most compact. So this one. See, on this one, the standard deviation would be the A would be a little bit bigger, and then on this one, B it'd be a little bit bigger, and then D would be have the greatest standard deviation. Oh, I was going to look at that one. the all right. So smartphones have a certain from a certain manufacturer have a mean lifetime of 62 months with a standard deviation of 12 months. The distribution of life times is not assumed to be symmetric. So that's why we have to use Chebyshev. So it essentially works like this. All right. Let's see. So one standard deviation, I think it's standard. I gotta look it up real quick just to make sure. I think one standard deviation is 75. I'm sorry, two standard deviations is 75. That's it. Okay, so where did it go? So what we got to go is we got to do down two standard deviations. All right. I'll just put that. So two standard deviations is at least 75%. Okay. So we got to just subtract two standard deviation and add two standard deviations. So 2 SDs is equal to 2 times 12. So 24. So 24 is two standard deviations. So we're going to do 62 minus 24 and 62 plus 24. So it works the same way as that empirical rule, or they call it there, the what is it, the 68, the 95, and the 99.7. So one standard deviation is 68, two is 95, and three is 99.7, or almost all of it. But with Chebyshev, it's slightly different, and it's just an inequality, they call it. So at least 75% is going to be between two standard deviations. There's really only two of them. There's two standard deviation and three standard deviations is 89%. So then what are these going to be? So there's the one, the left-hand one. So then here's our value. It's between 38 and 86. All I did was to find 75%, you go two standard deviations.
That moment when you
So
realize it's easier.
so 89%, 89% is three standard deviations. So if it said 89%, then you would just multiply 12 times 3 or 36, and then subtract 36 and add 36.
I must have been staring at the computer too long yesterday because that seems a
Yeah,
lot
I mean, if
easier
you look at
than
it,
I was doing or thinking that it would be. So thank you.
mm-hmm. All right. So I probably should have taken this out. This is the same calculation as the standard deviation. It's just that you don't take the square root, and they call that the variance. So let me just see if the mean is real easy. If the mean comes out even, I can knock this out. 6. If not, I'll come back to it. Okay, good. Yeah. So it's again population. I don't think they use sample in here, but we'll see. So then the mu is 9. So this one won't be too hard. And again, the only thing that's different, we just don't take the square root at the end. So 6 minus 9. So we're just subtracting that mean from everything. So then that's going to be -3, -6, -5, -2. I'm sorry, this is +5. And this is 5 again. And that's +2. And if you add up the negative ones, you would get -6, 7, 8, 9, 10, 11, 12. And then you add up the positive ones, 5, 2, and 5. That's +5, 12. Well, just realize that that's normal. All of these deviations will always add up to 0, because what you're finding, if you calculated the mean correctly and you did the subtractions right, then it'll be equidistant. Half of your data is going to be negative and half positive. So then I'm going to square these real quick. 9, 36, 25, 4, 25, and 9. And then to add all these up, so 108, so that should be the square root of 108. There's no square root. It's just variance squared. It's just sigma squared, because you're not taking the square root of it. So it's 108. And it was how many pieces of data? 1, 2, 3, 4, 5, 6. And what does that come out to on me? So 18. Good. So this one, the variance is before you square it. It's called the standard deviation when you square that value. In other words, sigma, or the standard deviation, would be equal to the square root of 18. Two runners, let's see, Dakota and Janie want to find out who has the faster time when compared to each of their teams. So the smaller standard deviation would be the better one. Okay. Anytime you're comparing. So you're just going to look for the one that's the smallest. So Dakota has a standard deviation of 0.1. And so she is doing better in terms. So Dakota's score is 0.13. That Dakota's score time is faster when compared to the team. So this is kind of the same thing as that one that you had, Brandy, given me, except it's the empirical rule. So with this is we know we're using that empirical rule, which is the 68. See, it's this one here. Or more appropriately, this one here. The 68, 95, and 99.7. So one standard deviation is 68. Two standard deviations is 95, and 3 is 99.7. So we got the mean, and we got the standard deviation here. All right, so how many standard deviations does it take us to get from the mean to the endpoint? Well, I'm just going to use a calculator. So take that mean, 1204.9, and I'm going to add the standard deviation. And then we're going to add it. So that gives us up to 13. We need to keep going to get to 14. Let's add another standard deviation. And then that gets us up to, so that's 2 standard deviations. 2. And 2 standard deviation is 95%. You can also see it on the other side, because if you subtract, and I'll just kind of show you real quick. The standard deviation was 124.6. I'm going to multiply it times 2. And I'm going to stick it right there, and then I'm going to subtract it from, and see, that gets me to the 55.7. So again, 2 standard deviations, and 2 standard deviations is 95%. So the number of miles driven by drivers at the delivery company is normally distributed and averages 210 miles per day, 210 miles per day. Devin drove 21 miles in one day, which is 3 standard deviations low as the median. What is the standard deviation of the miles driven? Okay, so we got to know what we're dealing with here formula-wise. And to calculate the z-score, z is equal to x minus the mean over the standard deviation. Now, what I'm going to do is I'm going to fill in each one of those that I have. All right. So 181 210. And then we don't know what the standard deviation is. We just know how many there are. So that's what we got to find out. So they're telling us here that it's 3.7 lower than the average. So that means it's negative. So now let's just simplify this a bit. So 181 minus 210. So that's negative 29. And an easy way to solve this is over 1, so we can just kind of multiply across. So they'd be negative 3.7. Oops, I need to just put the little sigma thing. So there's our variable there that we don't know. So now I'm just going to divide by both. And then that tells us, because this is the difference between the two values. And then we're just going to divide that difference by the standard deviation, and that's going to give us the number of standard deviations. And then we went to the tenths, 7.8. All right, so this basically just tells us this this little information right here. That just means that the mean is 11 and the standard deviation is 0.5. The n means that it's approximately normal. So all this is just saying that it's normally distributed with mean of 11 and standard deviation. So this is your mean, and then this is your standard deviation there. So what does that mean? Well, the mean is 11, and the standard, oh, sorry, I got it backwards. Oh, we got to calculate the standard deviation. We got to calculate the z-score. I'm sorry. So 12 minus the mean. So 12 minus 11 is 1. So this is smack dab 2.0. The z-score when x equals 12 is 2.0. The mean is 11. The z-score tells you that z equal tell is 2.0 standard deviations to the right because it's positive. Oh, and this is my little drawing thing that I had gotten. I didn't know it was in here. The graph below shows the graphs of several normal distributions. So on each one of these, you're looking at two things: the standard deviation and the mean. Okay, so the smallest standard deviation again is just the one that's squinched up the most. So it's that one right there. This has got the big fat standard deviation. This is in the middle, and that's the smallest one. So it's B. Let's see if we can get this 20 to stop at All right, Aaron's score on a standardized test is 3.9 standard deviations higher than the mean. The test scores are normally distributed with a standard deviation of 20 points. If Aaron scored 375 points on the test, what is the mean? All right, so we basically got to use the z-score formula. So we're using the test on the standard deviation. So 21. We know that it's 3.9. And then she scored 375. So what is the mean? We're just going to leave that with X and figure everything out. So again, the best way to handle this is just like two proportions. So that means we can cross multiply. So 1 times 3.75x is just 375 minus x, because multiplying by 1 doesn't change it. And then here, $81.9. All right, so then we're going to subtract 375 from both sides. So negative x is equal to negative 293.1. And then multiplying both sides, we're just changing the negative sign. Makes both of them positive. So 293.1 would be what the mean is. All right, so enough until next hour. Anybody got anything?
No, thank you. See you at 12:30.
You.
Okay.